Seeing it? So are you seeing the screen?
Yeah, I do.
Okay, so I will start the video now.
Welcome to our presentation on fully distributed peer-to-peer optimal voltage control with minimal model requirements. This is joint work with Alexander Prostejovsky, Heussen, and Saverio, Bolognani. Let's first have a look at the problem that we're trying to solve. Imagine you have a distribution grid with a point of common coupling and a long line connecting an electric vehicle, an inverter, and a wind or a solar park, so somehow some renewable generation. And with this active generation, we have an overvoltage at the end of the line. At the same time, the electric vehicle might be charging, leading to an undervoltage here. And now the question that we're asking ourselves is, how do we use the reactive power capabilities of the inverters to make sure that the voltage is within the feasible voltage set at all times that we define from 0.95 to 1.05. And at the same time, we also want to make sure that the reactive power set points of the inverters are within their capabilities. We define this as our volt var problem. So for every inverter H, we want to find its reactive power set points such that the voltages are all within the voltage range and the reactive power set points are also within the capabilities of the inverters. Right now, these problems are solved locally with local controllers. So every inverter just takes a local voltage measurement and then decides on its own reactive power set points. Those controllers have nice properties, which are there's no communication involved, they don't need any model information, and only inverter measurements are used. Unfortunately, those are suboptimal, which we are going to see later. There are quite a few papers out there that do this local control, and the three I highlighted here are actually the grid code. So manufacturers of inverters are actually asked to include local controllers for their reactive power set points. And the question that we're asking ourselves is, does communication allow to achieve optimality, which these local controllers don't have? And from other papers, we see, yes, that is the case. Once we introduce some kind of communication, we can recover optimality. What we want to do today is we want to do a systematic way of designing this communication so that we achieve optimality. How are we going to do this then? We're going to start it off with an optimization problem. So we're going to try to find a queue that satisfies all these constraints that we had. And we also want to minimize some cost function at the same time. Why do we choose this specific cost function? Because we're going to use techniques from distributed optimization that will lead to a feedback controller that is distributed and has some kind of communication in it to achieve optimality of the problem. So how to distributely solve this optimization problem? And first, we're going to start by dualizing the constraints. So we're going to introduce the multipliers lambda and mu, which are going to be associated with these inequality constraints, and we build our Lagrange. Then we're going to do dual updates. The first is the lambda update. So we're going to do lambda t plus 1 is going to be the old lambda t plus some step size alpha times the derivative of the Lagrangian with respect to lambda. So we're just going to do a gradient ascent in lambda, and that's a normal procedure that we know from optimization techniques. We also introduced this bracket operator around this term to make sure that this dual variable is always going to be positive because it's a dual variable associated with an inequality constraint, and therefore it always has to be positive. Luckily, if we evaluate this derivative, then we see that the derivative of the Lagrangian with respect to lambda is actually just the voltage violation. And therefore, what the lambda update is, it's just a local integration of the voltage violation at each specific inverter. And the same applies for our mu update. For mu, we do exactly the same thing. We take the Lagrangian with respect to mu, we do a gradient ascent, and here we have different step size gamma, but the rest stays the same. We're just locally integrating the voltage, the constraint violation, which in this case is the reactive power violation. And then the last update that we need to do is the update of Q. So our actually our reactive power set point. And this, because we dualized all the inequality constraints, we have now an unconstrained quadratic program. And the solution to that is quite easy. You can see the details in our paper. What we're doing is we're solving the argument here. And what we get is to calculate the reactive power set points of the inverters, we multiply the identity matrix with the difference of these Lagrangian multipliers, and we add this matrix times the difference of these multipliers. The nice thing is now, if some inverter wants to calculate its own new reactive power set point, because we have an identity matrix here, it doesn't need to know the lambda values of the other inverters. And because of the sparsity of the grid, G is a matrix that has zeros in it. And so to calculate the next Q, every inverter only needs to know the dual multipliers mu that are associated with these non-zero entries here, because there's no need to communicate something that we're going to multiply by zero anyway. And so for a specific network that we're analyzing in this paper, that we're going to have hardware results for later on, we have that the PV2 only needs to communicate with the electric vehicle and the battery, so with both other nodes, but the electric vehicle doesn't need to communicate with the battery and vice versa. And that's the reason we have a zero here and a zero here. And therefore, if the electric vehicle wants to calculate its new reactive power set point, it only needs to know its own lambda values, its own mu values, and the mu value of PV2, which is going to be multiplied with this minus 40 here. And so because G is sparse, our communication is also going to be sparse. Let's have a look at a block diagram of this. So down here, we have the distribution grid, and every inverter takes a local voltage measurement. Then does the mu update, and then it does Q and mu updates back and forth, and the mu updates are always going to be communicated to the neighbors. In the end, then the PV1 and the PV2 and the battery, all the inverters are going to apply their new reactive power set point to the distribution grid, and then the whole thing starts over again. Let's take a look at this in a timeline. So at time t, we take a measurement and we do one lambda update. Then we do k times a mu and a q update, always back and forth, k each. Then we are going to actuate the system with our new reactive power set point, and then we're going to wait for a few moments, and then we're going to take our next measurement. The whole thing starts over again. Now let's have a look at the hardware that we implemented this on. Through the Quadratic Program, we were able to have access to the SysLab laboratory of the Technical University of Denmark in Roskilde. And what you can see here is the overview of the SysLab laboratory. We have 4 different buildings that have bus bars in them. Connected to these bus bars are all kinds of different devices, and we can connect these bus bars with all kinds of cables. And we use this laboratory to build the topology that I showed you earlier. So an electric vehicle that we build from a PV inverter and a static load, some PV inverter here that we use to use its reactive power capabilities, and a battery in the end. We use the battery and not a wind park or a solar farm, because then we could repeat the experiments always with the same active power. So marked here with these eyes are the inverters that we used. The cable colors here correspond to the colors that we see here on the right side, and the grid connection is the transformer down here. We used the battery at an active power at 10 kilowatts, and the static load was running at 15 kilowatts, and the reactive power capabilities, the battery and the PV inverters were plus minus 8 kilowatts and plus minus 6 kilowatts. Let's have a look at experimental results for a Droop controller, which is the local controller that is currently recommended in the grid codes. What we can see here in this figure is 10 minutes of measurement data on the x-axis. On this y-axis, we see the reactive power injected by the inverters, and on the left y-axis, we see the voltage at these inverters. In the beginning, we have this large overvoltage due to a large active power injection of the battery. At minute 3, we activate our controller. The battery sees the overvoltage and then reduces its reactive power to its minimum value. This lowers the overvoltage, but it's not enough to bring the overvoltage back into the range of lower than 1.05. PV2 doesn't see an overvoltage, and it's inside its dead band, and therefore it doesn't do anything. PV1 actually sees an undervoltage that is outside of its dead band, and therefore it tries to increase the voltage here by injecting reactive power. And this makes the overvoltage at the battery even worse. So unfortunately, because we do not use the reactive power of the PVs, we do not converge, and we do have a persistent overvoltage at the battery, which would mean that we would need to curtail the active power. And if this was a solar farm or a wind farm, then we would need to curtail renewable energy, what we really don't want to do. Also, because the local controller at PV1 injects reactive power, it actually makes the overvoltage worse, which means that we would need to curtail even more active power, renewable active power, because of the local control at PV1. In difference to this, we can see the results here of our distributed controller. Again, we have the overvoltage in the beginning, and at minute 3, we activate our controller. What happens first is that the battery sees the overvoltage and starts integrating this overvoltage in its lambda update. As long as there is an overvoltage, this lambda update is going to integrate this voltage violation, and the reactive power is going to go down and down until it hits the reactive power limit of the battery. Once it hits this reactive power limit, then the mu update becomes active, and the mu values are going to be different to 0. These are then communicated to PV2, and then PV2 starts reducing its reactive power. Once the reactive power of PV2 is at its limit, then the dual multiplier mu of PV2 is going to become positive, and then this is communicated to PV1, and then PV1 starts reducing its overvoltage, reducing its reactive power, and as long as there is a voltage violation at the battery, the reactive power is going to go down until at some point we're going to converge exactly to the voltage limit. Once we step the active power of the battery back to 0, the voltage of the battery is going to go down, and also all the reactive power set points of the inverters are going to go back to 0 because there is no need for voltage regulation. And so we have convergence to the allowed voltage band, which is exactly what we're looking for. Now let's look at the scalability of this approach. Up until now, we only had 3 nodes in this communication scheme. And what we're going to do now is we're going to analyze what happens if we add n-dummy nodes in between. Why do we do dummy nodes without any active or reactive power capabilities? Because then the optimization problem still has the same solution and everything stays the same. So here we're just looking at the communication and the problem setup if we have more nodes. So let's first recall how this algorithm works. First, we have a measurement and a lambda update, and then we do k times these q and mu iterations back and forth. Then we do an actuation, and then we start over again. We're now going to ask ourselves whether we need more of these iterations k if we add dummy nodes, so will k need to be larger? And also what happens to t plus 1? Will it take more of these measurement to actuation to measurement steps until we converge to the voltage band? Let's first have a look at the iterations k that we need. What we can see in the first column here is the number of nodes in our system. So 3 nodes is just without any dummy nodes what we see. And here we can see how many communication steps we would need, so how large k would need to be if we wanted to converge to the optimum of this sub-problem of iterating between the mu and the q update back and forth. So if we do that 35 times, then that converged. If we have 7 nodes, we need more communication steps, and if we are at 100 nodes, we actually already need 20,000 communication steps. But because we do all these steps, then the actuation steps don't really change. So from t to t plus 1, we would only need to do that 50, 60 times to converge to the voltage band. However, if we would only do 1 communication step and then do an actuation step and then do 1 communication step again, then quite fast we wouldn't need a massive amount of actuation steps, so steps from t to t plus 1, and therefore a convergence take a very long time. And so we can conclude that if we have more nodes, we need more communication steps, but it's not an exponential rise, and therefore we think the algorithm is scalable. Now let's have a closer look at what happens for the case with 30 nodes. We know that if we do nearly 15,000 iterations of the mu and the q update, then we can converge within 51 actuations. But what happens if we're not doing all these 15,000, but we're doing less? And this is what we're going to see on this slide. So for the 30 bus case, if we do 30,000 iterations of the mu and q update back and forth, we are going to converge in 51 steps. If we are not doing that many, but we're actually only doing 1,000 or 300 q and mu updates back and forth, then the number of actuation steps until we converge rises, but it doesn't rise too much. And so we can conclude that we have faster convergence with larger k, and k should be as large as possible, but it doesn't need to be very large. And this brings us to our conclusion. First, all local control strategies can make over and under voltages worse, as we saw. Peer-to-peer communication enables convergence to the optimal solution though, and this communication should happen more often than the actuation, and the whole approach scales nicely with the number of nodes. Now I would like to thank my co-authors again, Alex, Kai, and Saverio. And last but not least, I would like to acknowledge our funding. We were funded by the Horizon 2020 program of the European Commission that enabled us to go to the Technical University of Denmark through the ARIGRID project. And with this, I would like to thank you for your attention.
Thank you, Lukas, for your very good presentation. So we have you alive now for questions. Can we hear?
Yes.
Yeah, you are there. Okay.
Yes, I will. I'm happy to answer any questions. The first one is from Adonis again, and he's asking, can you comment on the dynamic and steady state stability guarantee of this approach? Let's first talk about the steady state guarantees. And with this basically optimization algorithm that we're running in closed loop on the system, we can guarantee that we're converging to the optimal solution of the problem that we defined. To be honest, when we're defining the problem, this is the problem that we're defining, we choose a special cost function M, which is going to be the inverse of this G matrix that I introduced. So we're kind of solving a special problem, but it's basically what we're trying to solve. The cost function here is we're going to penalize voltage deviations. So we're converging to the optimal solution. And I think the optimization problem that we are solving is a very reasonable assumption. On the dynamic stability guarantees, we are going to assume that every time we set a set point, the system is going to converge to its new steady state very fast with all the dynamics in there, which are probably going to only going to take a few milliseconds. And because we're only actuating every second, or in our experimental setup, we were actually only able to actuate every 10 seconds. But that's not due to the algorithm, but due to the hardware. And with that within that time, everything converged, and therefore we won't have any dynamic or steady state stability issues.
Okay, I think this is a good answer. Okay, I just realized, Lukas, that I didn't introduce you, so sorry for that.
No.
Lukas is a PhD student in automatic control. The Automatic Control Laboratory of ETH in Zurich. He obtained his undergraduate and graduate degree in electrical engineering from RWTH Aachen University in 2014 and 2018 respectively. And during his graduate studies, he was a visiting student at the University of California, Berkeley, and also conducted research in the Doyle group at Harvard University in Cambridge. So sorry for not introducing you, but the thing of the video kind of distracted me. So we don't have any other questions from the audience, so I will take the time left to ask you for a comment on the slide that you are showing at the moment, and that in which you right, that you are minimizing a quadratic function of the reactive power, right? So there is a reactive power function that is quadratic that you are taking as your objective function for the controller. And the question is, why are you minimizing a quadratic output function of the reactive power? Why are you squaring it?
Because then the derivative that we're going to take on the next slide here.
Yeah. Okay. So it's just for the mathematical computation convenience, right?
So it is nice that in the end, then we get a very easy and convenient controller. On the other side, what I already said is that if you actually multiply q times the square root of m, and then the square root of m times q again, then what you actually get is going to be the voltage deviations between the buses to the power of 2. And therefore, we are penalizing voltage violations. We could also do this with a 1 norm, where we are just going to sum up the different voltage violations, or in the Q points here. But then the derivative would be different. It would still be implementable, but if you go for the quadratic version, then you end up with these nicely distributed controllers.
Okay, but from the engineering point of view, would it make more sense to use a linear function than a quadratic one, right?
Well, it depends whether you are, I mean, the advantage of having something quadratic is that you are acting on large deviations more than on small ones.
And why does that make sense from the practical point of view? Why should I care more about two kilovars in one unit than 1 kilovar in 1 kilovar per unit? It's the same, right? You don't have to answer. This is just a comment, okay? We are running out of time. Thank you, Lukas, so much, and sorry for not introducing you.
Don't worry.
I will not make the same mistake with the next speaker. So please, can you stop sharing your screen?
Yes,
because we are
sharing my screen, and if anyone is interested in this, there's actually a second presentation of mine in an hour or so.
Okay,
yeah,
great. Okay, thank you, Lukas.
Thank you.
So the next speaker is Dr. Terry.